A note on the Bateman-Horn conjecture. The Bateman-Horn conjecture was proposed in 1962 by Bateman and Horn, based on earlier work by Hardy and Littlewood and many others. The conjecture said, for prime numbers generated by a set of irreducible polynomials f1, f2, fn, which all have integer coefficients and leading positive coefficients, the number of primes generated by these polynomials have the following asymptotic formula. It's proportional to C, which is a Bateman-Horn constant, divided by the product of the degree of all these polynomials, multiplied by this integral. The Bateman-Horn constant C is an infinite product of all the prime numbers. Here, m is the number of polynomials involved. Omega fp is the number of solutions to the congruous equation fn equals 0 mod p, where fn is the product of all these irreducible polynomials. In this paper, we proposed a modified version of the Bateman-Horn conjecture. Our modification said the prime number distribution function pi should be asymptotically proportional to the same Bateman-Horn constant times an integral, which is now slightly different from the old version. This integral now has in its denominator the product of the log of the polynomials. The Bateman-Horn conjecture is still open today. In our paper, we provided some heuristic argument why we want to modify the conjecture in this way. For the rest of the paper, we tested our newly proposed conjecture on 6 selected polynomials. The first polynomial is simply the twin primes conjecture. The second polynomial is the Solfaing-Germain primes. The third polynomial is a quadratic polynomial, and the fourth polynomial is also a quadratic polynomial, also known as the Cuban primes. And the last two polynomials are two cubic polynomials. Our main conclusion of the paper is that for non-monic polynomials, the newly proposed form of the conjecture is much more accurate than the original form of the conjecture. As an example, let's look at the empirical results on the two cubic polynomials. In this table, the first column, these are the different values of x. And this column tabulates the actual counting of number of primes generated from this polynomial. And we count these number of primes using the software SageMath. And this column tabulates the number of primes calculated from the newly proposed version of the conjecture. And this column contains the number of primes calculated from the original version of the conjecture. As you can see, when compared with the actual counting, this newly proposed version of the conjecture produces results that are much closer to the actual counting than the older version. And similar results can be seen for the second polynomial. Here is the actual counting using the software SageMath. And here, this column is the prediction from the newly proposed version of the conjecture. And the last column contains the numbers from the original version of the conjecture. As you can see, the newly proposed version of conjecture is much closer to the actual counting using SageMath than the original version of the conjecture. Furthermore, the accuracy holds for a wide range of x values, which seem to suggest that the newly proposed conjecture is not just simply an asymptotic formula. It seems to be valid over a wide range of x values. And this is very similar to the classic polynomial theorem, where the logarithmic integral is a much better approximation to the prime counting function pi of x than the asymptotic version x over log x. Thank you very much for watching.